So, I'm Richard Steenbergen. This is a tutorial on Guide to Peering. So the things that we're going to talk about: what is peering, why do networks peer, where and how networks peer, a little bit of understanding of what are the motivations behind people that peer, why they peer with certain people, a look at various peering policies and requirements that you're likely to see, talk about some peering strategies and techniques, and then say, does peering make sense for me? So the first question, obviously as a tutorial, is what is peering? So to understand peering, first we have to understand how networks interconnect with each other. So we all know or should know that the internet is just a collection of individual networks that interconnect with each other under a common framework of global reachability. So there's unique addressing, and everyone knows how to route to those unique addresses, but it's really a collection of individual networks that are all talking together. And there's really three primary relationships that these interconnections take. The first one is a provider. That's someone that you pay money to, who has the responsibility of routing your packets to the entire internet. The inverse of that is the customer. That's someone who pays you money with the expectation that you will deliver their packets to and from the entire internet. And then the third main relationship type is the peer, which is two networks that get together and agree to exchange traffic between their two networks only, typically for free. So here's a really simple peering scenario. You've got a couple of providers. Provider B and C here don't talk to each other. They both buy from provider A, and they both have customers, and they have some number of customers that connect to each one independently. There's some number of customers that buy from both. And what happens right now is when traffic goes from one customer to another, it goes through provider A. So the really simple peering scenario for these two networks is, hey, why don't we exchange traffic with each other, and then we don't have to both pay provider A, so they establish a peering session. That's the simple, best case, easy scenario. So there's obviously a bunch of benefits to peering. The big one is reduced operating costs. You're no longer paying a transit provider. And since peering traffic is free, in theory at any rate, this is going to reduce your transit bill. There's some potential for improved routing. You're no longer being forced to send traffic from B to A to C. You have a direct interconnection. So you're eliminating a middleman. You're eliminating a potential point of failure. And you're also increasing the distribution of your traffic. So instead of having one transit provider, you may now have many different peers, and you're spreading out that traffic over many different destinations. So you can improve your ability to scale and potentially improve the reliability of your network. So the first thing that people talk about when peering is exchange points. So what is an exchange point? An exchange point is just a layer 2 network where multiple network entities meet for the purposes of connecting with each other. This may be called an IX, Internet Exchange. It's also called public peering. Historically, they were called NAPs. The term doesn't really apply anymore. But today, most exchange points are just Ethernet-based LANs where every member shares a common broadcast domain. So for example, there might be a single /24, and every member has one router that gets one IP on that 24, and they all talk to each other over that connection. And exchange points are typically dedicated solely to facilitating peering. So the people that run them really want to promote peering. They're not there to sell transit. They're really not there for much else other than promoting peering. So why do people peer at exchange points? The number one reason is because they serve as a common gathering point. When you want to get out and start peering with someone, your first question is, who do I peer with and where do I find them? And an exchange point acts as a gathering point for like-minded people that want to get together and peer. So when a network is new to peering, they're usually going to go to an exchange point first because that's where they can find dozens or even hundreds of networks that want to peer with them. And the more members an exchange point has, the more valuable it becomes. So this is commonly referred to as critical mass. The more people there are in one place, the less likely you are to go somewhere else in that region. So you end up with, ideally, one place, maybe two places for redundancy where everyone gathers, and then you don't have to go deal with multiple buildings, multiple exchange points, provisioning. It simplifies the process. And the exchange point is really about simplifying the process of peering. Because it's a multi-point system, you don't have to do any work when you want to turn up a peer. You don't have to go provision a new cross-connect. You don't have to go configure a port on your router. That's all done for you the first time you turn up the port. So all you need to do to turn up a new peer is just configure a BGP session. So typically the cost model for that is you pay a monthly cost for the port, and that's it. So the more peering you do, the more attractive the price on your exchange point becomes, and the better it is as an investment. So on an exchange point, there's two main ways that you can peer with people. It's called bilateral and multilateral peering. Bilateral peering is just two networks who get together and negotiate a relationship between only themselves. So when I establish a BGP session to my neighbor who I want to peer with, we're peering bilaterally. A common feature of exchange points is multilateral peering, which is usually an exchange point operated route server. What happens there is, instead of having to connect to 100 different people, maintain 100 different BGP sessions, you set up one or two sessions to a route server, and it's effectively the same as peering with everyone else who wants to be there. So it's for people who are completely open peer. They want to peer with everyone, and they want to make the process as simple as possible. So anyone that connects to this exchange automatically peers with you, and there's no work required. And that's called a multilateral peering exchange, or MLPE. And I basically described the rest of it. It's just a way to simplify the process. But at the end of the day, there's a lot of inherent limitations with exchange points. One of the biggest is that it's a single layer 2 network, and it's relatively easy to disrupt. And modern exchange points are pretty reliable. People put a lot of time and effort into making them work well. But at the same time, a layer 2 network is inherently fragile. And if anything goes wrong, what tends to happen is it takes out the entire exchange and takes out every member. So you see situations where a card fails and starts broadcasting traffic. You see a member misconfiguration. You see a spanning tree misconfiguration. There's any number of ways that you can go wrong. And in some cases, not only can it take down your entire exchange, but depending on the kind of router that you own, it can actually take down your entire router. For example, if you've got like a Cisco 6500 and you start getting flooded with broadcasts from an exchange, it's probably not just going to take down that port. It's probably going to take down the whole box. So that's a big consideration for people. It's relatively difficult to measure the traffic that you're exchanging between members. So modern exchange points have a way around this, typically S-flow. And what this does is they measure sampled packets between individual MAC addresses, and they have a portal where you can go log in and look at graphs and see how much traffic you're doing. But this isn't billing grade material. So you're limited in what you can do with the data. You have to go through their portal to use it, and it's really difficult for people to measure traffic on their own routers. Even if your router does have the correct MAC accounting capabilities, typically those ports end up being very expensive, and it's difficult to configure. There's a lot of routers out there where you don't have any visibility into how much traffic you're doing. So you connect to an exchange and you hope that it's working well, but you don't necessarily have that visibility. And there's still a lot of exchange points out there that don't have any kind of an S-flow portal. Another major problem is that any member can communicate with any member whether you want them to or not. It's just a big open LAN. So what can happen is it's really easy to have security issues or theft of service issues where someone points a default route at you or starts doing things to disrupt your router, steal service from you. And it becomes a big consideration for bigger networks, especially because there's ways that you can mitigate this, but it turns out to be really expensive. You end up having to have very expensive routers or dedicated routers for peering edges. No matter how you do it, you end up spending a lot of money to make it work. Scaling layer 2 networks is inherently difficult. So the bigger an exchange point gets, the more difficult it is to continue to scale and continue to offer the same service. So a lot of times you end up seeing big exchange points where they have more core trunk ports that are inside their network that are blocked due to spanning tree than they have customer ports, because that's what's necessary to maintain a redundant network. And they end up spending a lot of money for that overhead, and they end up passing that cost on to you. So there's an inherent limit to how much traffic you can do over an exchange point relative to the size of the individual links and how much complexity, how much chassis and inter-chassis connections and things like that you need. Most exchange points really have little or no control over the traffic that's being exchanged. So you might peer with someone, or you might peer with 10 people, and one peer might be sending you enough to congest your port. You have no way to stop them from doing that, and your other 9 peers are going to be affected. They're going to say, why am I getting lost to you? Oh, well, this one peer is overrunning my port. Or the bigger problem is you might be overrunning their port, and you don't have any visibility into that. You don't know when their port's full. You don't know when they're upgrading or not upgrading. You're at their mercy, and communication is not always the best. And ultimately, also share broadcast domains. It's not as easy to set up redundancy. Everyone does one router at an exchange point, but once you start wanting to set up multiple routers, diverse connections, it's not easy to do. You really don't get the same level of redundancy when you start adding more connections. And then ultimately, you reach a point where when you're passing a lot of traffic to a certain peer, the overhead of the exchange point is simply going to be too high. I mean, there's a lot of overhead in running this layer 2 network, which is designed for connecting to a whole lot of people. And if you have big traffic flows to one specific network, ultimately it's not the right way to go. So what is the right way? You get into private peering. So private peering is just a direct interconnection between 2 networks using a dedicated transport service or fiber. It's also called a private network interconnect, or PNI. Typically inside of a data center, what you're going to do is order a dark fiber cross connect. It might be copper, but typically it's fiber. It could also be a telco delivered circuit as well, but people try to stay away from those. Historically, that's how people did PNIs. They would order an OC12 from their LEC to interconnect 2 buildings, and people realized that this was extremely difficult and hard to provision capacity, cost a lot of money. So it was a lot easier for people to come together under one roof, deploy routers in one building, and then just do a cheap fiber cross connect and upgrade the links whenever they need to. And often in private peering, the cost of the interconnection itself is shared. So a typical model for doing this is, I'll buy this one, you buy the next one, that kind of thing. So the next question is, well, what should I be doing, public or private peering? And there's a lot of considerations. An exchange point is an optimal choice for interconnecting to a large number of small networks. You minimize the overhead, the provisioning overhead, but you lose scalability. So that's the optimal point for it. And if you were to try and maintain a bunch of private interconnections for small peers, and just give an example, if you maintained 100 individual gigi cross connects to talk to a bunch of peers that were 100 megs, 200 megs, 300 megs, 400 megs, the cost of those cross connects ends up adding up quickly. And it's probably going to be more than the cost of the exchange point to do all these individual low-speed cross connects. Not to mention the cost of your router ports, the cost of their router ports, provisioning time, configuration overhead. But a private peer is a much more optimal choice when you have 2 networks that are passing a lot of traffic. So for example, if you had 2 networks that were passing 10 gigs of traffic, or 9 gigs or 8 gigs or something close to that, it's probably a lot easier for you to provision a dedicated 10 gig port and a lot cheaper than it is for you to each buy another 10 gig on the exchange point and continue passing traffic that way. And the reality is most networks, at least most smart networks, actually maintain a mix of both. There's a time and a place for each. And the amount of one that you have versus the other depends on the size and scope of your network. But people that only do one or only do the other often find that they're limiting themselves for artificial reasons. So the next thing to talk about before I get into policy stuff is the concept of mutual benefit in peering and why it matters. So most peering relationships are for mutual benefit. That means I get something, you get something, we both agree that we should peer. It's a healthy relationship. That's almost always the case. There's some situations where people are required to peer for regulatory reasons or things like that, but the vast majority of peering relationships really are for mutual benefit. And if it doesn't benefit both parties, then it probably shouldn't exist, and eventually it probably won't exist. The question is, what constitutes mutual benefit? Some people say, as long as we both benefit some. Other people say the benefit has to be equal to both networks, or else one side should be paying. But here's just a little example for people to understand mutual benefit. So consider this example. You have a hammer and your neighbor has a saw, and you both need both tools for some home renovation projects that you're working on. So rather than you go out and buy the saw and your neighbor go out and buy the hammer, you get together and you say, hey, why don't we loan each other tools, and that'll save us money and we'll both benefit. At that point, everyone's happy, everyone's benefiting equally, and it's a natural relationship. Now, imagine over time, your neighbor ends up purchasing a bunch of additional tools and you don't. So at this point, your neighbor has 30 different tools and you still have only a hammer. At that point, it may not make sense for your neighbor. He may not consider it fair that you want to come over and borrow all his tools and the only thing you have to offer is a hammer. Now, imagine what happens when your neighbor buys his own hammer. At this point, it's no longer not even fair. It's that there's no benefit for him at all. He gains nothing. He already has a hammer. He has no need to have this relationship with you. The only thing that he sees is the cost of managing this relationship and the time that you're borrowing his tools. And he might still let you get away with it because you have a pre-existing relationship, or just to be nice, but as long as the burden's minimal. And if you start being a pain, he might reconsider that relationship. Now, imagine what happens if your neighbor goes into the tool renting business and he's actually charging other people money for loaning out his tools, and you still continue to borrow all of his tools without offering anything of your own. And not only that, but you borrow his tools and then you rent them out to people that he would otherwise be renting them out to. You're no longer just a nuisance. You're now an active competitor. You're a liability. And he's probably not going to continue that relationship. So a lot of ways this summarizes how peering relationships are seen. And people need to understand when they say, so-and-so should be peering with me, maybe they shouldn't. Maybe they have a legitimate reason why not to. So talk about peering policies. So the first thing that a network that's new to peering learns when they go out to peer is that not everyone wants to peer with them. And just the way to summarize the general kind of status that a network has as far as their willingness to peer, we break it down into 3 categories. The first is open, which means they're generally willing to peer with anyone or almost anyone, maybe not people that have to send them a copy of their router configs and don't know what to type, but anyone that is reasonably willing to peer, they'll peer with without imposing any kind of specific tests or conditions. Second category is selective, and that means they have a set of requirements that they test against, but they're pretty fair about it. If you meet those requirements, they'll peer. If you don't meet those requirements, they won't. And then the third category is restrictive, and that means the network is generally inclined not to peer at all. And they may still have a specific set of requirements, but that doesn't, A, necessarily mean that they'll honor them, and B, the way that they set those requirements is often intended to be higher than they think anyone can ever reach. So the goal is we're trying to appear fair, but the reality is we don't want to peer with anyone. And it's really important for people that want to get into peering to understand not just what the other network says their policy is, but what their actual thinking is. What are their motivations? Why would they want to peer with you? Why would they not want to peer with you? And all too often I hear people go, oh, that network, they don't want to peer with me. They're just jerks. And sometimes that's true, but the reality is if you can't get away from your position, consider what it's like to be that other network, and consider if it really does make sense to peer with you or not, you're not going to have a successful time in peering. You really need to understand what are other people's motivations. A lot of times these things go through phases. So when a network first starts to peer, typically their initial policy is open. It's because they don't know who to peer with, where to peer. All they know is that someone told them they should peer, or they think that they can save money by peering. And the default behavior is, well, let's peer with everyone, let's offload as much transit traffic as possible, peering is good, go peering. Eventually, as the network grows, they come to a point where they realize that you don't necessarily need to peer with everyone to get the same results. There's no benefit to peering with a customer of a customer of a customer, or peering with a customer of a customer of a peer. You've already got that route. You're not increasing your reach. And in a lot of ways, you're decreasing things because now you have to pay to haul to that one peer, whereas if you passed it over your much larger, bigger peer relationship, you might be interconnecting in multiple locations and have a stronger relationship. So people at a certain point start to impose requirements. They might be size, scale, composition of your network, amount of traffic, things like that. But at the same time, they're open to peering with people that meet their requirements. And then as a network grows still larger, and there's been a lot of networks that have gone through all three of these cycles, all the way from completely open to tier 1, they reach a point where they say, well, we already peer with everyone that we need to peer with. Why do we need to peer with anyone else? And they reach a point where when they start consolidating traffic down, rather than peer with 500 peers, if they peer with 100 peers, or they peer with 50 peers, they do more traffic over those fewer number of peers, and so they end up with a stronger relationship. They have more capacity, more interconnection. They peer with more people. That gives them more routes. And at a certain point, once you reach the point where you say, well, I've kind of already peered everyone that I need to peer with, the networks start to see these people as customers rather than peers. And they don't want to give away something for free that they think they could charge for. So here's some example peering requirements that you'll see in the real world. One of the big ones is backbone capacity and diversity. And this makes a lot of sense purely from a technical perspective. You don't want to peer with a network that is significantly smaller than yours, to the point that they don't have enough capacity to haul the traffic that you're going to send them. They don't have enough capacity to deliver the traffic. They don't have redundancy. They can't survive a fiber cut. They can't survive a power outage. At a certain point, it doesn't make sense, and you're actually decreasing the quality of your network by doing that. So people institute these simple requirements, backbone capacity, diversity, things like that. Another common one is minimum number of locations. This also has a lot of technical merit. If you operate, for example, a nationwide network and you want to peer with someone else that operates a US-based nationwide network, it probably doesn't make sense for you to peer in 2 locations. Everyone in the middle of the country is going to have horrible latency. You're decreasing the quality of your network. So you hit a requirement to have a certain minimum number of locations and diversity, and it makes technical sense. You want that network quality to be there. You want the diversity to be there. You want the redundant paths and the low latency to be there. You start getting into requirements like POP requirements or number of region requirements, and that's not. You're not saying, I want to peer with you in 5 locations, but you're saying you must operate a network in 47 states, even if I don't peer with you in 47 states. And kind of what you start getting into there is imposing requirements on the size of the other network from a business perspective, not necessarily traffic or technical anything, but you're just trying to limit the scope of who you peer with. Typically that's one that you'll see in a lot of more restrictive peers where they really want to limit it to only other very large networks. You'll see traffic requirements are a big one. This has technical merit, but this mostly has policy merit. Maybe it doesn't make sense for me to configure a BGP session where the BGP session does more traffic than the actual traffic being exchanged. And there's a number of situations like that where it doesn't make sense. So people set a minimum traffic requirement and they say that's where I need to draw the line. You need to have at least this much traffic to play in this ballpark. That's how it is. Major peering requirements, consistent routing is pretty universal. There's some networks that don't require it, but most do. And what this means is that they want you to announce the same routes with the same attributes across all locations. And they do this because routing between peers is typically done as hot potato. That means you take the closest exit. You want to get this traffic off your network as quickly as possible. And if someone were to send you different attributes, or they were to send you one route in, for example, San Jose, but not Ashburn, your network is now responsible for hauling that traffic all the way to that prefix, and that's not the hot potato relationship that most peering relationships are built on. So if both sides don't agree to this as an exception, typically the default policy is going to be, we want to see consistent routing, and if you don't do that, you're in violation of policy. Another big requirement is no simultaneous peer and customer relationships. There's a lot of reasons for this, but there's one really big one. It's actually pretty easy to rig the BGP announcements to get free transit if you talk to a network as both a peer and a transit provider. And policy reasons too, it probably doesn't make much sense to do that. So people just impose this rule, you can't simultaneously be a peer and a customer. And that has technical merit. There's historically been a belief with a lot of network that once you're a customer, you can never be a peer. And there's some people that hold on to that, but that's generally not the case these days. If your network reaches a point where you qualify as a peer and you're no longer willing to be a transit customer, there's only so much that the other network's going to do to not give you peering. There's your basic operations requirement, 24/7 NOC. Is a common one, maximal acceptable response time for network issues. The bottom line is no one wants to peer with someone that doesn't respond when there's an issue. When I've got a circuit that's taking loss and I email your NOC and you don't answer me, it's impacting both of our networks. So there should be some general response time. Both sides should be willing to commit resources to operating their network correctly. There's your generic peering requirements, which is announce only your customer prefixes. That's the basic definition of peering, but you'll see that in peering requirements. That's just don't do anything stupid. Don't point static routes, don't point defaults, don't alter BGP next hops. This is really, gets into the territory of theft of service at that point. You're no longer using the routes that the other party is sending you. You're now nailing up other routes and using them for transit and not paying them. So they start to have problems with that, obviously. There's your basic good neighbor requirements, which are, for example, you must prefix filter your customers. And really that's just, it doesn't do anyone on the internet any good if you are a BGP speaking network who lets your customers announce anything they want, because if people start believing your announcements, you're going to potentially create hijacking, you're going to create all kinds of outages. Each network should be responsible for filtering their own customers, so you'll see that in peering requirements. The same thing for you must be responsive to spam, denial of service, and other abuse issues. No one wants to be peering with someone who's running a network that's full of spammers and hosting all kinds of malware and things like that. And it comes back on them. Why are you connecting to this network? Why are they not responding to these abuse issues? So you'll see that in peering requirements. Some peers require a non-disclosure agreement. They don't want to talk about details of their peering. Other peers don't. It varies depending on peers and what their policies are, how anal their lawyers are, things like that. But the other thing that you'll see is term lengths. So some peers will have like a term. Let's say we will review this contract once a year. But most, probably the vast majority of them, have termination clauses where they say this peering can be terminated by either party for any reason, typically with X days notice. Like that might be 30 days. That's just, you come to a point where the peering relationship no longer makes sense, there's no longer mutual benefit. You need to give the other party some time so they can prepare, but at the same time you can't necessarily be bound to keep this peering relationship up forever if it doesn't make sense for you. And then we come to traffic ratios, which is the requirement so infamously gets its own section. So traffic ratios are extremely popular by the networks that use them, and at the same time hotly contested and hated by the networks that don't like them. The concept is really simple. You measure the amount of traffic that you send versus the amount of traffic that you receive, and what's the ratio between the two. So the question is, why do people care about traffic ratios? In a peering relationship like we talked about before, traffic is going to be hot potato. That means I want to get my traffic to your network as quickly as possible. You want to get your traffic to mine as quickly as possible. So what that means is the person that is taking the traffic inbound typically has higher costs associated. They haul the packet across the majority of their network, and the other person hauls the packet over very little of their network. So if the ratio is 1-to-1, both peers haul the same amount equally, and it's considered beneficial, or it's considered an equal relationship. But you get into a situation where if network A is very push heavy, and network B is very pull heavy, network B ends up paying most of the cost, and network B might consider this unfair, and that's where you see traffic ratios. So here's just kind of an example. You've got a content network in Los Angeles sending to an eyeball customer in Chicago. Your traffic going one direction is going to be this big 1,500 byte packet that the inbound network is paying to haul, and transport is usually one of the most, if not the most expensive component of running a network, so there's real cost associated with this. And then in response to that 1,500 byte packet, your network only has to haul a 40 byte packet. So obviously this network is going to say this isn't necessarily fair. But there's a lot of arguments against this as well. And there's a lot of people that really argue that it doesn't make any sense. So for example, what happens if network B in this example is actually pull heavy overall? It's not really network A's fault that they're sending traffic to network B, because network B has eyeballs that are requesting the traffic. You can't send traffic that doesn't exist. You can't receive traffic that doesn't exist. So if you are peering with a network that is imbalanced, it's natural that your traffic is going to be imbalanced. And sometimes the network that is imbalanced is going to insist on a balance ratio anyways, even when that doesn't make any sense. Network A at that point may believe that network B is just using ratios as an excuse not to peer with them, or they might be using ratios as an excuse to make network A haul their traffic, or whatever the reason may be. There's no technical merit at that point. CDN traffic also disrupts the simple analysis, because if you look at the way CDNs work, CDNs, content distribution networks, typically spend a lot of money and infrastructure costs to replicate the content closer to the edge. So they may not be paying circuit costs, but they're paying server costs, they're paying colo, they're paying power, they're paying cross connects, they're paying, what does it take to distribute that content out to the edge. So they can easily be paying as much or more than another network. It's just that you don't see it in the simple analysis of ratios that we were talking about in the other slide. And so even though the ratios are high, the balance may actually be quite fair, especially considering that a CDN is you're not only having a fair distribution of costs, but a CDN is actually reducing your costs. It's completely eliminating them. You no longer have to backhaul traffic, period. So maybe that should be considered fair, but a lot of people don't see that. They stick to these strict definitions of ratios, and they say, well, I've been told that an even ratio is required, and so that's what I want to see. And ultimately, the argument comes down to, does it really even matter that the costs be equal? Imagine if network A is charging $10 a meg and network B is charging $100 a meg for the same bit that one person is pushing to the other. Why isn't network B willing to pay 10 times the backhaul cost, Ren?
It's probably covered later, but where do you factor in the cost of truck rolls?
Not talking about truck rolls to the residents, but I'm just talking about network backbone. It depends on your network. You might have a network that you pay huge residential costs to push that out to your residences, but at the same time, your residential customers are paying you money to do that. Yep. So this is an argument that people get into what is the fair cost? Who should be paying for this cost? Obviously, there is a cost associated with it, and that's the question is, who should be paying for it? Talk a little bit about network tiers, just for fun. Tier what? No. There will be no classical addressing. So people talk about tier this, tier that. A tier is an informal summary of the interconnection relationships of a particular network. So I say informal because there's no standardizing body here. There's nothing there's no definition. You can't go look this up. you can probably go look it up on Wikipedia, but you can't go look it up in a standards body and say, this is the definition. But this is the generally accepted definition that most of us toss about as engineers. A Tier 1 network is a network that does not purchase transit from any other network, and therefore they peer with every other Tier 1 network, and that's how they maintain global reachability. A Tier 2 is a network that has transit customers and does some peering, but they still buy some transit to reach some portion of the internet. And the reality is a Tier 2 can be everything from a mom and pop ISP with a 10 meg connection to an exchange point, all the way up to the biggest almost Tier 1, but they still buy transit from one network. It covers a huge range of networks. So you really can't describe much of anything with the name Tier 2. But it's out there. And then a Tier 3 is a stub network. It's typically without any transit customers, without any peering relationships. They're just a stub. And obviously, like I said, the key point is that these are informal. And so what ends up happening is these definitions get twisted by sales and marketing departments to find a way to claim that they are Tier 1. Everyone on the planet claims that they are Tier 1. Most of them aren't, but they'll claim it anyways. People will claim, oh, it's number of route fiber miles, it's number of continents, it's number of cities. They'll make stuff up depending on whatever their network is. But the generally accepted status we're talking about is how do they interconnect with other networks. So here's a highly, highly, highly simplified kind of diagram showing kind of like a Tier 1, Tier 2, Tier 3 relationship. And what you see here is that there's a much smaller number of Tier 1s than there are Tier 2s. There's a very small number of Tier 1s. I think right now it's something like 8, give or take, depending on how you prove it one way or the other. But there's a very small number of Tier 1s out there. They typically peer only with themselves, very few other people. They have their own customers. They have their own Tier 3s that connect to them directly. And they have a bunch of Tier 2s that connect to them. You look at Tier 2s, and what you see is that the Tier 2s kind of peer highly amongst themselves. They buy transit from some Tier 1s, but they, in many ways, can completely bypass the Tier 1s because they peer so densely amongst themselves. And there's a much higher number of them. And then they have their own customers that are single home to them. This kind of a generic diagram. So you get to a point where there's a distinction between Tier 1 and transit-free. We already talked about a Tier 1 network being transit-free, but that doesn't mean a transit-free network is a Tier 1. So imagine what happens in the following scenario. Say that you go out and buy transit from every Tier 1. There's not that many of them. You go call them up, you buy transit, and you announce your routes, and you tag them with a BGP community that says only export to your customers. You're simulating a peering relationship. It's not a settlement-free peering relationship, but you're simulating route propagation of a peering relationship. At that point, you can be transit-free. You no longer have transit from anyone. But does that make you a Tier 1? Probably not. So to be a true Tier 1, the definition is always that you need settlement-free peering. But the problem is any settlement that's being paid between networks is easily hidden by NDA, and no one's going to talk about what that is. So it's really difficult to objectively prove who is a Tier 1 and who isn't based on that analysis. But at the same time, you can't just wash your hands of it and say, well, it doesn't matter, because you can very easily have a network go out and do exactly the scenario that I described above, and they're not really a Tier 1. It's not that status grants them anything one way or the other, but that's not how they behave. That's not how they're treated. So in effect, they're not a Tier 1. And there's also some trouble with Tier 1s. Many people view Tier 1 as the ultimate end goal. And you know, it sounds good on the face of it. Settlement free to everyone sounds good, right? No transit costs. But there's a lot of limitations that this imposes on you. So by definition, a Tier 1 must peer with or sell to every other transit-free network in order to have global end-to-end reachability. So if there are two transit-free networks that were peering with each other that discontinue peering, those two networks become partitioned from each other. The internet no longer functions as the internet. You no longer have global end-to-end reachability. And your customers on both sides are impacted. And without a transit provider, there's no backup plan. There's nothing that you can do. If you're a Tier 1 or you're a transit-free network and someone de-peers you, what are you going to do? You're going to sit there with an outage until one side or the other caves and turns the session back up, or one side or the other peers. And really what this does is it hurts the customer. And there's a lot of tier ones that have peering requirements that explicitly forbid hearing the announcement from other paths. But even if a tier one was willing to go out and buy transit, at that point they would probably be de-peered by the other tier ones, because they're proving that they're no longer equals. They're no longer able to stand on their own. So you end up with these little disputes and fights amongst tier ones back and forth, and they're severely disruptive. So it's not always sunshine and lollipops. Get into the topic of paid peering a little bit. Paid peering is just like regular peering, except that one side pays the other some kind of settlement for the privilege. In some circles, it may be called partial transit, but the name partial transit, just like a tier one and transit free are not the same. Partial transit could mean any relationship that is not transit. That doesn't necessarily mean customer routes only. So using the term paid peering is a lot more specific. You're addressing one very specific relationship. And it covers a really wide range of situations, everything from two networks who are very, very close to meeting each other's peering requirements. They're razor thin close, but one side just needs that little extra kick to make them do it. You know, it could be a very small cost. It could be paying for the ports. It could be paying a very nominal fee for the ports. It could be paying a nominal price per meg, all the way down to two very dissimilar networks who would never peer with each other in a normal situation, where one side says that, hey, I'm not willing to pay you for transit, but just like you sell transit as a product, I would buy peering from you as a product. I'll pay you a price per meg and you deliver me the service, and it's just not the full routing table. And there's a lot of reasons for that. So some of the typical arguments in favor of offering paid peering if you're a provider. As a provider who is peering with someone, you're being paid twice. You're being paid by the customer on the other side of the bit, and now you can be paid a second time for the paid peer. So it's called double dipping, which just means, luckily enough, someone's paying you to haul the traffic across your network, which may or may not be a good thing, because hauling traffic is actually pretty expensive, but at that point you're getting paid twice. If your customers are multi-homed and you go out and offer paid peering solution to people and it's a cheaper or a better product, what happens is you can incentivize others to use your network. And so the person that's pushing the traffic has complete control over where that traffic goes. They can set their local path however they want. I can send my traffic to A, B, or C. And if A is giving me a better price, A is going to get my traffic. And so that starves B and C of traffic and revenue, and it helps network A. And so they might be willing to go out and offer that as a solution to draw traffic into them, make their network bigger, increase their revenue. On the customer side, there are some advantages to doing it. As a settlement-free peer, you're kind of at the mercy of both sides having availability of ports. And you get into the situation where you might peer with a network, and you might both be equal peers, but you go, oh, this port's full, I need another one. And the other peer says, oh, sorry, we're out of CRS ports until 6 months from now. Suck it. Which happens. But if you're a paid peer, you've got some prioritization. You're paying money for some kind of a service, and you can kind of demand that you get the ports that you want when you get them. So you may be treated as a customer, but that might help you. That might guarantee that you get some level of availability, whereas if there's no revenue attached to it, it's harder for these networks to justify infrastructure upgrades and port costs and provisioning new ports when there's no revenue attached to it. So sometimes it's actually worth it just to pay a little bit of money to be done with it. There's a lot of arguments against offering paid peering. One argument is that traffic that's a paid peer, someone sending you traffic that's going to your customers, That, by definition, means that you're going to haul that traffic across your network. If it was off-net traffic, if someone sent me traffic to send to another transit provider, that traffic could very easily come in one router port, go out the other router port, and it costs me nothing. But if someone is sending traffic to my customer, that pretty much guarantees that I'm going to have to haul that on my backbone, which costs a lot of money to provision, a lot of money to upgrade. You're guaranteed there's going to be costs associated with that. And transport costs are typically very high, and they're typically higher than the cost of transit, specifically because a lot of people know that when they have a transit cost, they're hot potatoing that traffic right off. They don't have to pay to backhaul it. You end up with customers that want to purchase this non-standard product. And typically there's a reason for that. There's a reason that someone wants to buy paid peering from you. One reason might be that they need to appear to be directly connected for political reasons. Their customers want them to think that they have a settlement-free peer or have a direct connection to big eyeball network. Or they want to give the appearance of having that, and so they're willing to pay for it. And a lot of times they're willing to pay a premium, or even if they're not, that's what comes to the mind of people that are pricing paid peering products. They say, why should we give this out to everyone? If you really want it, maybe you should pay us more for it. And then you get into a situation where customers intentionally buy from networks with restricted policies, hoping to motivate others to peer with them directly. So for example, if I think that Sprint has a restricted policy and I go out and buy from Sprint, specifically because I think that you don't peer with Sprint and that's more likely to make you want to peer with me, maybe I don't want to buy from Sprint anymore if Sprint gives cheap paid peering away and all of a sudden it doesn't look like that's the situation. Now it looks like this network got peering with Sprint, and I, as an outside party, have no idea. I don't know that they're paying. It looks to me like it's a peer, and so that motivates me not to use Sprint as, in this example, as a restrictive transit provider. Okay, so now we get into peering strategies. The first one is donut peering. And the principle behind this is that the majority of the internet is multi-homed at some level. Even if the end customer is not multi-homed, they connect to an ISP. That ISP is probably multi-homed. Even if that ISP isn't multi-homed, they connect to an ISP. That ISP is probably multi-homed. At some point, the vast, vast, vast majority, like 95% or more of the internet is multi-homed. There's a way to get to a particular network. You can choose between A, B, or C. There's always some kind of a choice. And so the situation is, if a particular network doesn't want to peer with you, you can work around them, and that's called donut peering. So for example, a large Tier 1 network can very easily, and most of the Tier 1 networks have 100,000 customer prefixes, but if you actually look at what those prefixes are, typically only around like 5% of them are single-homed customers who you have to use that network to reach. The other 95%, you could peer with them directly, you could peer with another one of their transit providers, you could do any number of things to bypass that restrictive Tier 1 or whoever has that restrictive policy. And it turns out that this technique is actually really effective. And what you see today is a lot of Tier 2 networks that do more traffic than the classic Tier 1s. So kind of what you end up seeing is that the Tier 1s become the stronghold of, we're going to hold on to this restrictive peering, we're going to charge a premium for this traffic, you have to use us to get to this 5%, but at the same time, everyone else is growing faster than them, everyone else is doing more traffic than them, bypassing them completely, and so, yeah, you may still need them to get to some portion of the internet, but more and more huge portions, huge eyeball networks, huge content networks are able to bypass paying these guys completely and have direct relationships. Like I was talking about earlier, a classic technique is to buy from a restrictive peer. The technique there is really simple. If I buy from someone who's a restrictive peer and the person that I want to peer with doesn't peer with them, they're more likely to peer with me. They're going to go, okay, yeah, you're behind Sprint. I don't want to pay Sprint. Okay, fine, whatever, we'll turn it to peer. If you're behind an existing peer of theirs, they may have no reason to peer with you. You're already behind an existing peer. You contribute nothing new. And similarly, if you started buying transit from someone that they already peer with, they may notice that and then say, hey, I could de-peer you and I could drive that traffic over to this other link. Maybe I shouldn't be peering with you. So buying from restrictive networks is a very, very classic technique for increasing peering. A increasingly popular technique is to intentionally create bad routing. So it's kind of taking it one step beyond a restricted peer. Not only are you saying it's going to cost you money to reach me, but now you're saying there's no amount of money that you can pay to reach me. I'm going to intentionally make sure that my transit providers are saturated, or that the path that you're taking to me is suboptimal. I'm going to announce routes in such a way that I'm going to make you haul the traffic from San Jose to Chicago back to San Jose. I'm going to do something to create impact. And it's not a complete and total outage, but it's suboptimal. And then your customers are going to go to you and start complaining, hey, why is your performance so bad to this network? And you might say, okay, fine, we'll peer just to solve this situation, improve performance, fine, whatever, let's just do it. Some networks use this technique to drive sales instead, where what happens is even if a network that they peer with or want to peer with doesn't peer with them, that network's customers might come to you directly and say, okay, fine, I'm willing to buy transit from you just to resolve these performance issues. The problem is that this technique really can easily backfire. Because you're not just hurting your potential peers' customers or this third party's customers, you're hurting your customers too. And if your customers have a choice and they can pick up and move to someone who isn't screwing with their traffic, they're probably going to do that. And what happens is networks who engage in this kind of activity very quickly develop a reputation, and that reputation sticks around for a really long time. So even many years after a network decides to stop doing this, there's people out there that still know them as, hey, wasn't that network that was always congested to everyone for 2 years? And you lose customers as a really long time as a result. So there's a lot of people that have tried this and realized that there's some short-term gains, but the long-term losses might actually be worse than the short-term gains. Another classic technique to increasing peering is to have a restricted policy yourself. And you might ask, how does having a restricted policy get you more peering? The answer is networks that have really open peering policies. If I peer with 500 people, I might be sending 500 different people 100 megs of traffic. If I consolidate that down to 50, now I'm sending them a gig of traffic each. And so now I'm able to get on the radar screens of these other networks. I'm doing more traffic. They're going to notice me. They're going to be willing to peer with me. You're just increasing the size, the amount of traffic, and a lot of networks do this to manage their ratios. For example, if you're a push-heavy network with a lot of content and you want your ratios to be better, it's probably not a good thing for you to go out and peer with someone who is also a push-heavy network, because what little inbound you did have, you're taking away from potentially sending that over another peer to help your ratios. And people find that strategic peering is often more effective than open peering. Like we talked about, you can motivate other networks to peer with you because of increased traffic. You can also motivate them by saying, hey, rather than me going out and peering with your customers, how about I not do that? I'll just peer with you. Would you then be willing to peer with me? And there's a lot of networks that say, well, okay, that's an attractive offer. I will be willing to peer with you. So it's kind of an anti-donut policy. Rather than specifically avoiding a network, you're specifically targeting a network who's willing to work with you. You're increasing their total traffic. You're increasing what they can bill their customers, and you're defeating the donut. Another classic technique is to tie your peering to other purchases. Just because you don't want to pay money for transit doesn't mean you can't pay money for other things. There's a lot of networks that buy things other than transit. It might be fiber, it might be transport, waves, circuits, colo, any number of other services, other business relationships that you can have. And you can go in and say, okay, I want settlement-free peering, but in exchange, I'm going to give you this particular colo deal, or I'm going to buy this fiber, or I'm going to going to outsource my dial to you. There are any number of situations where this comes into play. And the large networks, you are generally able to do this kind of thing. They're able to tie this other purchasing into a settlement-free peering relationship. And even if you aren't necessarily doing it immediately, you might be able to tie it in and say, all right, I'm going to promise to give you 3 years of transit revenue now, but at the end of my 3 years, I want a clause that if I meet these specific conditions, you have to give me peering. And so the network says, well, I wouldn't normally give you peering, but you're giving me 3 solid years of revenue. Okay, that makes sense. I'll be willing to do it. So then we come to the question is, does peering make sense for me? And I have two fun little quotes from anonymous people who will not be mentioned. But basically, this peering thing ain't so easy as the people profiting from it make it out to be. Sums it up. So in theory, peering is free, right? Free. The reality is not necessarily. There's a lot of overhead that comes with peering. And you can very easily get into a situation where the overhead is higher than the cost of just buying transit. And many of the people who are out there rah-rah, cheerleading, go peering, they're not actually doing it for your best interest. They're not doing it to save you money. They're not doing it to increase your performance. They're doing it so that you buy a service from them. So you have to look at this with a really critical eye and say, does peering actually make sense for me? Or are these people that are promoting it out for their own best interest and not mine? You need to consider when you peer, what does it actually cost you for that router or that switch port? What does it cost you for that cross connect? What does it cost you in engineering man hours to configure and maintain those peers? What does it cost you when there's an outage and you have to wake someone up in the middle of the night to work on them? What does it cost you to maintain a backbone and to backhaul traffic that you might not have to do if you just bought transit? What do you lose in 95th percentile aggregation? And I meant to have a graph here that illustrates this, but people that understand how 95th percentile works, the billing, what you're paying for is almost the peak of your traffic. So if you have, for example, traffic that's going to a European ISP that peaks over here at this time on the graph, and you have traffic that's going to an Asian ISP that peaks over here on the graph, and you look at them individually and you sum them up, you get 1 plus 2. But if you put them together, you only get 1. You get this much flatter graph, so you aren't paying for that peak. So you got to look at what are you losing in 95th aggregation by splitting all this traffic up among all these different networks. What does it cost you in lost traffic with a transit provider, where if you did a lot more traffic, maybe you could go to your transit provider and negotiate a better price for all of it. You really need to take this into consideration. So just as a small example, let's say that you privately peer with 10 networks using 10 individual 1 gig ports, and let's say that those cross connects cost you $300 a month. And you also publicly peer over an exchange with a 10 gig port, and that exchange port costs you $3,000 a month. The really simple answer is the cost there is 30 cents a meg. But that's not true. That's only true if you're using 100% of those ports, which you're probably not. No one can run their network that way, especially with peers where you don't have the flexibility to select what traffic you send over the peer or not. Most people tend to find that if you may have one peer that's at 80%, you may have one peer that's less, but if you kind of look at your overall numbers, most people tend to find that they actually have an average of about 50% utilization on their peers. So now your cost is not 30 cents a meg, now your cost is actually 60 cents a meg. But what would happen if you combine that 95th? Like I talked about, if you have trafficked all these different individual networks with very different peaks, what would happen if you combine that onto one single transit graph? And the reality is, a lot of people tend to see another 50% gain or loss, depending on how you look at it, from mixing or not mixing that traffic together. So what did it cost you for those router ports? What did it cost you for that engineering time to configure and maintain those peers? And the reality is that if you could go out and buy transit traffic at $1 or $1.50 or something along those lines, it might dollar for dollar actually be cheaper than your 30 cent a meg peering, or your free peering if you think of peering as free. Then we get to the dark side of peering. The way that peering works is the first, people tend to say the first 50% is easy. Maybe not necessarily 50%, but the first some percentage is easy. It's the low-hanging fruit. You go out, you find the people that want to peer with you, you want to peer with them, everyone's happy, it's a peering love fest. You immediately decrease your transit traffic, and it's very low overhead. It doesn't cost you much to provision a connection. You're there, they're there, everyone's happy. But after you hit that point, you start going, well, okay, I want to peer some more. And you start to realize that the next peers are harder to get. You've got to do more work. You've got to spend more money. You've got to be in more buildings. You've got to buy more backbone capacity, more waves, more routers, more circuits. You've got to meet their peering requirements. It starts to get really difficult really quickly. And people don't always take this into account. They say, well, peering is fun. They look at it in a lot of situations more as something to do or an ego thing and not necessarily a business relationship. And so you need to keep in mind when you're deciding whether you want to peer or not, does this make financial sense? And what happens if the costs change? What happens in 6 months if transit costs go down, which they've historically always done? What happens to any number of these costs? Building out a peering network specifically locks you into a very specific path. And then if you really step back and look at it and you wonder how much of the bad routing, congestion problems that are on the internet are actually caused by peering, the reality is it's actually a lot. We talked about all the situations where people buy from restrictive peers who don't want to peer or don't want to upgrade, creating congestion, people that intentionally create bad routing, people that don't maintain their peers well, people that don't have ports available for upgrades and run the circuits hot for months at a time. The reality is that a lot of times you're causing a lot of impact to your customers. And the reality is if the other network is willing to cause disruption to their customers until you pay the money and you're not willing to cause disruption to your customers, then in peering parlance you lose. You have to pay. So a lot of times it turns into a game of chicken. It turns into how long can we continue to stab ourselves in the foot until one person says, this hurts, I think I'll stop. And that creates a bad situation for everyone. While you're out there creating poor routing and buying from all these restricted networks, you may not realize that you're actually just hurting your own customers. So it's something to keep in mind. And that is basically all that I have. So questions? Anybody? Nobody? It should be posted. Okay. Not even questions from Ren? Okay.